Today I will explain the finite element analysis of the induction motor. This is with respect to magnetostatics. Magnetostatic means, do you know? Magnetostatic means the analysis of the magnetic field with respect to static. That means assuming the magnetic field is to be static in the induction motor. Let us start now. This is a FEMM. Go to the file and open new. There you will see the create new problem, magnetics problem, electrostatic problem, and heat flow problem, current flow problem. You can check clearly, get an idea in file. Okay, now select the magnetics problem and click OK. Now the white page will appear. Here, go to file. Once again, there are options open and import DXF file. Open if you have already FEMM file, then you can directly open. Here I have one file. I show this is FEM. If I open, this is I made it in FEMM itself. That is using the available tools. So if you are unable to use this thing, just close it and go to, and if you have already a DXF file that is created using an AutoCAD, then you can import that DXF file of geometry in FEMM software. Go to the import DXF. There you will see the available file, or choose wherever the folder you have been saved the DXF file. Choose that file and open. Here you can see clearly the CAD drawing.dxf. So only DXF file format will be supported in this software when you want to import. Now open the file. Here tolerance. If you want tolerance, you can fix it. Otherwise you can just make it 0 in order to have a clear DXF file. But FEMM won't support the straight lines, as we can see when you are importing a file. So it's better to keep tolerance as 0 to get a clear the curves. If you have used the curves and you after fixing tolerance to 0, just click OK. Here you can see there are lines or arcs with orphaned endpoints. You just click OK to continue. Now fit to the screen. So here you can see what is that straight lines. Here I draw the slots. I'll show at the end how it will be. Those lines are here. In order to clear these lines, just go to here and click OK. To select these lines, just right click it. And here you cannot use the mouse. You can use a keyboard to move down, or you can just zoom in and zoom out. Choose these straight lines, as we don't want these things. Just delete it. So still you can see the points. You can clear points by choosing a point option. As you can see here, the tools are available on the top. Now just choose it and right click whichever the points you don't want. Just I am doing, just watch. So there will be points here also where I previously cleared the line. Choose them to delete. Here are extra points which I don't want, so just I will clear it this thing. But since I want continuity, I just choose a line and select these 2 points, so it will become a line. Now, in order to draw the slots and teeth, just choose a line and choose the points, and you should be able to differentiate which is the slot and which is the teeth. Choose the corresponding points of slots to make it a slot and leave the space. Just continue as I am doing. Choose the 2 points continuously between the points whichever you require a slot line or to differentiate slot and teeth, and don't simply merge it. So just move. You should be careful while doing these things, because the reason is if you are unable to differentiate slot and teeth, what and what, then you will get a bad result, especially while analyzing, and you won't get expected result, even if 50% also. So you must be careful. These are whatever I'm drawing this stator slot. It's not the rotor. I'll come to the rotor later words. So let us complete at least one part. Now we are almost nearer to differentiate. See, you can see this part is the only slot, and this is the core, and this is the teeth of the slot. That means teeth where the magnetic field will be flowing, and this is the slot area where the windings will be placed. Still it is not complete because we will be fixing wedges on the slot, so you can complete by drawing lines similar to that itself. You need to have a continuity. Just do it by selecting same procedure of 2 points such that there is no break. You must be very careful while drawing these type of small lines because these are very important to differentiate the area. Area in the sense means medium, that is stator, rotor, hair gap. Otherwise, you are itself not able to predict. See, now I made a mistake. So points must be correctly chosen such that it will cover the clear area whichever you desire. Be careful while joining these things. Do it clearly and slowly. There is no hurry for anything. If you make hurry, then you will lose the result. So here you can observe that in core, that is I didn't connected the teeth. I just connected the slots, that is also at the bottom. The reason is the teeth and core is same material, so I need not to connect. If I connect this thing, this area becomes a different material to be filled. So in order to avoid that, I need to connect here. So in order to isolate those things, now let us move with rotor. This is the rotor point, and you should, if you know, this is the conductor. Since I taken rectangle, so I can easily identify this thing, and also I am completing directly. If you want, you can do it directly, but if you don't want afterwards, whatever the decision you take, you can carry out. There is nothing to worry. So I'm moving little bit faster because I am thinking that you would have been understand how to draw these lines. There is a toolbar option line, and you if you select two points, between those 2 points you will gonna get a line. That will be always straight lines, or if you want, you can also deviate by deviating the point positions. Since I am already available with these points, so I am not marking any points, just I am moving with lines. So that's it. You can continue. Here also I am completing this thing because these rectangles are the rotor conductors. I need to differentiate this rotor material because rotor is also made up of M magnetic material itself. That can be steel, silicon steel. There are different grades of silicon steel. So I will be showing when I am adding materials to these things. You are nothing to worry. And I am completing these things. Almost I am coming nearer. Let me show how the material library will work in Femm. And now here you can see two lines with small gap between stator and rotor conductors. This small gap is an air gap that you will be assuming or you will be calculating when you are designing a induction motor or anything. So that's what here you can clearly see. There is a small gap. When you zoom it, and you can clearly visible. Since as our eye persistence will be very low, so when you zoom out, it will be very small distance to see it, but nothing to worry. If you zoom, and it is clearly visible for you itself. So I'm just completing. I'm almost nearer to complete rotor slots, that is rotor conductors in itself. So I'm just completed with rotor conductors. Now you need to define a problem. Is it a planar or axis symmetric? Planar in the sense just it will be symmetrical, and axis symmetric means you will be knowing it won't be symmetrical with respect to any. Here the length units. Length in the sense the here you will be able to see only 2D dimensional object, but in reality there is a 3D object of motor. So you need to give the length, that is here are the different parameters: inches, millimeters, centimeters, meters, mils. So in AutoCAD we will be usually dealing with millimeters, so I'm going with millimeter. Here the frequency of operation, usually we will make with respect to 0 rather than fixing an frequency, because once you are, if you are able to see the DC analysis, then it is a small modification of AC. So depth, the depth is nothing but the unit, the length. I designed a induction motor of length for 14.8 centimeter, that is 148 mm. Here the solver precision. Solver precision is the whenever the FEMM starts its analysis, it will form a smaller triangles. So what must be the triangle size? That will be given by solver precision. The minimum angle, that is the triangle angle present. Here the AC solver of a successive approximation and Newton-Raphson. You can choose any two of these, but let us go with successive approximation rather than Newton-Raphson, because Newton-Raphson will always take it's a time consuming for you or whatever system, whatever maybe it is. So successive approximation is best when you are solving huge problems. This is problem defining. Problem is over. This is the grid, that whatever you are seeing here. Operations, node, segment, arc segment, that is these things are present here. This is the node, this is the line, this is the arc. And here the properties. Here you can see materials, boundary, point, circuits, materials library. So in order to add materials to this thing, so first go to this option and just click. Here you can see, and just go on doing this, and here also, and you need to add these things for each and everything of whatever the rectangles you have been drawn. So after adding these things, now just go to properties. Here go to materials, go to materials library. Here you can see material library materials. Here will be always given a highest preference, as it is almost occupies major role in the dynamics, or when you are analyzing magnetostatics. Here you can see PM, permanent magnet materials, soft magnetic materials, solid non-magnetic conductors, copper AWG, copper SWG, copper metric magnetic wires, metals, handbook DC, magnetization occur, 15% copper clad aluminum magnetic. So here are different. So since induction motor is an soft magnetic material, I'll go for it. And here you can see silicon iron. Just go to, these are the different grades of steel. Here I'm taking M19, and also add here, which is also required. Now go to the copper. Here I'm using SWG 16. So let me take it, just draw it, and for rotor it is a purely copper, so I'm taking these things. Just click the corresponding any material. Here you can see name, BH curve, linear or non-linear, and these things were all fixed. So here for 16 gauge wire, just change the now for copper, for solid you need to change, give the magnetic density, because you will be giving even though current, so it's better to give current density. Now click OK. So you are added materials. Now go to same properties and go to the circuits. Here go to add material. In the place of new circuit, press capital R that represent the first phase. Here parallel and series, whichever the connections you are using for pole coil connections, just go to, if you are series connection, go to series, if it is parallel, go to parallel, and give the corresponding phase current. I am using 120 amperes, so it is added. Now once again add different material, that is there will be totally 3 phases, don't forget it. Phase currents will be same, and also still now I am adding B RYB. So and also in rotor also I need separate, so I will take that current to be, let it be G, that is it be C. So rotor conductor whatever I am calculated is, that is bar current, it's around 164 amps. So click OK. Now click OK. Just these things, required things were over. The mesh option I will tell afterwards. Now I will show how to add the materials. Now go to this point and right click it. Afterwards here you can see the option, go to that. Here you will gonna get block type, whichever the material. Core is always a M19, so I'm added. There is no circuit because it's not a conductor. Okay, added. Similarly, now just go down. Here you choose it. These are all conductors. Go to same point. Now choose 16 go SWG, and here you in circuit go to different RYB are the 3 phases. You will be calculate, you would have been calculated the number of slots per pole per phase, and so choose the slots whichever is having R and different, just choose it. Now you need to give, for series you need to give the number of turns, that is turns in the slot. So you will be knowing the conductors per slot, so just divide it by 2 and you will gonna get. Here I'm taking 2 turns per slot, so click OK. Now you can see I'm taken 3 slots per pole, so this is R phase and 2 turns per phase, not 2 turns per phase, 2 turns per slot, that is totally of 6 turns per phase. Similarly, now go here, you can see the gap, so go to there and add a material here and click OK. Just now you choose here and just add. This is a copper. Go to C and turns, let it be 1, because only one conductor will be there and minimum turns will be also 1. And I need to mention another important thing, you can repeat this sequence once R is over Y and B. So next this will gonna constitute a north pole. Now you need to have a south pole also. What you can make for south pole means same procedure, but in turns you should not, you just choose it. In turns go to, I'm just showing, let it be Y. So here instead of 1 just make it -2. So that will, this -2 will gonna minus of turns will gonna constitute a south pole, where positive turns will gonna constitute a north pole. That means positive turns means the current will be flowing in a positive direction. A negative turns means it will be flowing in a reverse direction. And also just add rotor core material also, that is magnetic material. Just go to M19, add it, okay. And for here just this is a shaft position, so just choose no mesh. You can choose any material, but it's preferred whenever we don't use it, no mesh. And you can create a mesh. Now I will show the complete one which I have been made instead of this thing. So here you can see this is the boundary part. You can neglect this thing and you can consider only this thing. I completed by drawing each and everything. Here you can see R phase. So totally there are 3 slots per ball per phase with 4 turns per slot. You can see this is R, these 3 slots. These 3 slots are Y, and here these 3 slots are B. So this will gonna constitute a north pole. Now I need a south pole. For south pole what I made, instead of +4 I put at -4. Just you can see I'm taking closer. Just look, R, Y also. Okay, I hope you are getting. For copper rotor also you have to make like this, because there will be totally 4 poles. I'm just added these things. I'll just fit to the screen. After doing these things and settings, just go to here, the yellow. This is a mesh option. Now it will gonna create a mesh. So after doing this thing, now go to the next toolbar. This will gonna generate a analysis. Here you can see the generation of analysis. See, even though I given successive approximation, it is going for Newton-Raphson because of those angle. Here you can see next to the analysis option one specs, so it will gonna come. Now it is the result. See, here you can see the output window, and these are the flux lines, north south, north south, north south, north south. And in order to give a better view, go for this colored one. Here you will gonna see the flux density, show density plot, and here you can see the density of magnetic flux density. Here there is an option, the color variations. It will gonna give you the magnetic flux density at a given point. And in order to see that, just zoom it and keep your FEMM window here, and go here. You need to choose point and just press that point. You're gonna clear detail. See, flux magnitude, bx component, y component, and magnetic intensity also, x component, y component. Yeah, you will also gonna get the energy per volume, that is energy density, and current density. Current density in magnetic material will be 0, because it won't be conducting any current. So only if you choose slot, then you can see the magnetic. Here, see, here you can see this is a slot and this is a teeth. Here there is a magnetic, whichever the value, depending upon the value of current you are given. So this is over. Just fit to the screen. See, it will slowly generate. Now in order to calculate anything, just go to contour, select the respective contour. So this is magnetic material. If you want to plot, you can create uh, a line that is contour, because if you want only with respect to single points, just choose it, so that only for that area you will be requiring plot, magnitude plot. So just come to here, and now I will gonna draw the plot. See here, there are two options: normal flux density, tangential, magnitude, intensity, normal, same thing. So whichever, I'll just generally go. Here it will ask for resolution. You can whichever you like give and click OK. Here you can see the actual magnetic flux density plot. The contour however you are being chosen, like that only this plot will gonna execute it. So this is one thing. And cancel. This is output window. Here integration, just choose the contour. Now just select it, go to integrate option. Here you will be seeing age, magnetic field energy, hysteresis loss, copper loss, stator loss, torque, whichever you want be integrated. I just go for total current, and I chosen complete only the magnetic material, not the copper, so it is showing 0 amperes. So like this you can carry out, and you will gonna get the output results. This is only with respect to magnetostatics. And thank you for watching this video. I'm completing here.